Hello, welcome to the third video on the electricity revision for the IGCSE course. We left it off here at the end of the second video, and we're starting to talk about potential difference in parallel circuits. So this looks like a bit of a mess, but if you pay close attention, it's not as complicated as it looks. It's really a circuit that would look like this if you took away all the voltmeters. Then what you have is something like this. You have a battery and then a light bulb here, another light bulb here, and then back home, and then a second branch with the same setup but in another branch. So that's what you have, except they put in voltmeters everywhere. Put a voltmeter here, one here, one here, one here, one here. And so this is asking you, what do you think the potential difference is going to be across all of these different light bulbs? So this is your setup. That's your parallel circuit that you have. Current goes in this direction, as you should know, from the positive to the negative. And so let's talk about series and parallel for a little bit, and what the meaning of potential difference is in each one and how it splits up in each one. This is a parallel circuit, and they're asking us what the potential drop is here, there, there, and here. And for that we need to understand a few things about series and parallel circuits. I always have this analogy of water as flowing in a kind of loop with pipes and then falling through gravity. The water is here, and this pump brings it all the way up here, and this is the amount of energy that the pump gives to the water in the sense of height. In this example it would be gravitational potential energy that the water gains, but in our electricity circuits, this analogy of gravitational potential energy would just be electric potential energy. That's what it would be in circuits. And this energy that we give to the charge, that the pump gives to the charge, we normally give all of that the name of EMF, which is called electromotive force, even though it's not a force. It's got that name for historical reasons, not for logical ones. And that is corresponding to the amount of energy per unit charge. So a unit charge is called a coulomb. The energy per unit charge that the battery gives to every single coulomb, that gives, let me say that again, the energy per unit charge that the battery is delivering, that's what we call the EMF, and that's normally given in volts. So this could be 10 volts, for example, if we were talking about an electric circuit. That would mean that for every coulomb that passes the battery or the cell, 10 joules of energy, right? 10 joules of energy are given to each coulomb. What happens then with that energy? That energy is then given by the electric charge back to the circuit, or the components that it encounters in the circuit. More energy always given to the components with most resistance, and less energy to the components with least resistance. So let's see what's happening here. In the analogy with water, the water is pumped all the way up here, given a certain amount of energy, which we're going to call 10 volts for this example. So 10 joules is carried by each of them, of the coulombs of charge. And as the water, if we draw the analogy between water and charge, if you imagine the water dropping down here and then filling in at this point, and then dropping down, spilling over here and dropping down here, and then spilling down over here and going back to the beginning. That's really what's happening with the charge as it goes through the circuit. First it gets energy from the cell, and then it gives it back as it encounters different sections of the circuit. So for example, this drop from here to here could correspond to a battery with a lower resistance. Sorry, a bulb with a low resistance. This drop is bigger, so that would be a bulb with a larger resistance. And finally, this is the biggest drop of all, so that could be a really big bulb, or or maybe perhaps a resistor itself, or something like that. Any component has a resistance, so you will always have a drop in energy through a component. What's interesting here is to see that the potential drop between these three together, those three, each of these is called the potential difference between this point and that point, and it's also measured in volts, the same way that EMF is measured in volts. Each of these three drops, drop number 1, potential drop number 2, potential difference number 2, and potential difference number 3, when you add them together you will find that the sum of all of these exactly equals the EMF of the battery. Okay, so hopefully that makes sense. So what we're saying, if this is a battery and there are all of these light bulbs connected, in this case there's 3, then if this cell has an EMF of 10 volts, so I keep correcting when I say battery, because a battery is technically a number of cells, but this is a cell. So if this cell has an EMF of 10 volts, it means that the potential drop through this guy here, plus the potential drop through this one, plus that one, is equal to 10 volts, right? We talked about that in the last video. Hopefully that makes sense. And this is the analogy of what's happening, okay? You can't drop more height than what has been given to you. So there's no way the water is going to be able to drop down more than the water was first elevated in the gravitational sense, and the same thing with the electrons. They cannot give more energy than they have. Neither do they give less than they have. They don't suddenly stop here and say, that's it, that's all the energy we're going to give away, and we'll get back to the battery and then get on with it. They don't do that. They give all of their energy away before heading back to the battery, and that's why they always fall down to this level. Okay? Now, why is this important to understand? In series circuits, it's quite a simple idea, but in parallel circuits, it becomes a little bit more tricky. But if you understand that idea, there's no reason why it should be very difficult in this one. Look what's happening here. You have a certain amount of charge which gets given energy, receives energy from the cell. In this case it's water through the pump, but it's the same thing, the energy through the cell, and then it gets here, and when it's at the top of its energy level, look what happens. Suddenly it divides. There's two pipes. The water has now an option. It can either go this way or it can go that way, and it will go through both. How much will go through both? It will completely depend on the resistance of each branch. Okay, this branch will have a certain resistance for the whole branch, and this whole branch here will have a certain resistance for the whole of this branch. And depending on which one is bigger, that's how much water will go through each one. Okay, the water is that clever, or the charge in the circuit is that clever. So this is going to fall onto here, then it's going to overspill onto there, it will overspill finally onto there, and the same thing will happen here. We're not concerned with the relative amounts yet. We just want to understand what's happening. What's important to understand here is that it doesn't matter how many drops this second path has. I'm going to call this path 2 compared with this path 1. It doesn't matter how many drops. This could have an extra third drop here. There's no reason why it can't have an extra drop, and therefore have 4 drops in total, 4 drops in energy, and this one only has 1, 2, and 3 drops, right? Doesn't matter if this has less drops in energy than that one, or you can see it as less components. So for example, this could have 3 light bulbs while this one has 4, or maybe 3 light bulbs and a resistor, or whatever. Each component will see a drop in energy through it. So what I wanted to see here is that it doesn't matter which route you take, the overall change in energy, the overall change in electrical potential energy, in this case gravitational with the water, is the same. Both drop through the same drop, and the whole drop will be the EMF, right? They both drop through the EMF. So in other words, the potential drop between this point and that point there is the same as the potential drop between this point and this point there. You see, it's the same drop in both. Hopefully you can see that, which means that even though the current splits, one goes one way and the other one goes the other way, the potential drop, the total through here and there is the same. So if this was 10 volts of EMF given to the charge, then the drop through one and through the other, the total drop will be also 10 volts for the total drop. Okay, except let's say all the light bulbs are the same for the sake of argument. The 10 volts will be spread here between only 3, so each one will get 3.33 volts of potential drop through them, while this one divide between 4, so this one will get 2 volts through them instead of 3.33. Sorry, not 2.5, right? 10 divided by 4 is 2.5. So each of these will have a 2.5 potential drop through them, and this will have a 3.3 volts. Why do they get more? Because there's less of them to share the total drop of the 10 volts. Okay, so what we're saying here, if we look at this circuit, is that as the current goes from here to here, if you compare the potential drop between here and here, if you measure that by plugging a voltmeter, which is how we measure potential difference, this will have to be, if this is 10 volts of EMF, this will have to read 10 volts. Okay, but what we're saying is that not only is that true, hopefully that makes sense just from the series circuits from before, but also if we put a voltmeter onto these two wires, okay, we'll also get a potential difference of 10 volts. In other words, you can put in 10 of these branches and they will all get as many volts as the EMF is offering. How much does each light bulb get? Well, that depends then on the relative resistances between the light bulbs. Light bulbs with more resistance will get more volts through them, or across them. It's a better way of saying it than through them. So that will, if you put a voltmeter here, it will read something. If you put a voltmeter here, it will read something different if these two resistances are different. But if they have the same resistance, these two will read the same, and it will be 5 volts. Why 5? Because they need to add up to a total of 10. Okay, if I connect a voltmeter from here to here, this is the same as connecting it from here to here, or the same as connecting it from here to here. It's the same exactly, because at this point it's already gone through both bulbs, so that should read also 10 volts, the full 10 volts. Hopefully all that makes sense, and we can move on to the next slide. Well, actually we can go back to the slide, solve this one, and then move to the next one. So here it is, 1.5 volts total EMF. So what are we going to get in each of these? Well, as we said, from here to there, it's got to be the full drop. Okay, we're talking about the drop of the full we're talking about the drop from the very beginning to the very end, right? So it's got to be the full drop, the same as the EMF. So if that's 1.5 for the full drop, then it's got to be 1.5 between here and there also. And so if we look at this, it's going to be 1.5 divided by these two. So it will be 0.75 here and 0.75 there, both adding to 1.5, which is the total. And down here is the same again. From here to there, it's got to be 1.5, so that will be 0.75, and that will be 0.75 volts. Hopefully that now makes sense after using the idea from the analogy. What about this guy? Well, it's got to drop 1.5 between here and here, because that's what it says up there. The EMF of the cell is 1.5, so this has to drop 1.5. This guy is lucky because he gets all of the whole drop for himself, so that would measure a voltage of 1.5 for the potential difference. These two would be sharing, and that would be 0.75 and 0.75. But the total drop through these two and through that guy has to be the same. In other words, 1.5, which is the EMF of the cell. Next, a little exercise which you can do by pausing the video now and thinking about what word from here you would place in those spaces, and I will now solve it for you. Please make sure you've paused it and tried giving it a go before you listen to me do it. Okay, so it says the something something of a component is a measure of how much something is something in the component. So that's two words, and that's already a clue, because the only thing here with two words is this here, potential difference. So the potential difference of a component is a measure of how much energy is transferred in the component. Okay, as we said before, how much energy is transferred between when the electrons are over here and when they are here, that's how much potential difference is across that component, that light bulb or whatever you've connected there. The potential difference across the cell must equal the sum of the potential differences across the components in a series circuit. Okay, and now we've used everything. It's interesting that they say series there. Why do they say series? Because in a parallel circuit it's not true that works so easily, because in a series circuit, yes, this plus that plus this, all of those potential differences, 3 volts, 4 volts and 5 volts perhaps, depending on the resistances, so this one would have the biggest resistance. Those three added together, 5 plus 4 is 9 plus 3 is 12, have to equal the EMF of the battery at GCSE level, because we assume that the battery doesn't have a resistance. Now, why is that not true and so simple in a parallel circuit? Well, let's think about this for a sec. There are your bulbs. If this guy here has a potential difference of 2 volts across it, this one has a potential difference of 4 volts, then this guy has to have one of 6 volts, because that branch and this branch have the same drop. But it's now not true that 2 plus 4 plus 6, which is 12, will be equal to this. This is not true. Why? Because they are in parallel, and so it's only one of the branches which you need to add to figure out how much energy drop there is from one branch to the other. It's going to be just one of the two branches, which is the 6 volts. 6 volts EMF will produce 6 volts across here, 6 volts across there. That's why this sentence here wouldn't work for a parallel circuit, so that's why they say series. Okay, hopefully that makes sense, and we can move on to the next one and summarize, because we need to close the video and then go to the next one. We're running out of time a little. So, current and potential difference summary. Again, I'll let you pause it for a second, think about this, and I'll do it in a sec myself, so pause it now and give it a bash. Okay, in a series circuit, what happens to the current? Current is something at any point. The current is equal at any point, okay, because if you think about this here, the current through here, the amount of water that's going around is always the same, so it's the same here as it is here. So here, if it's running there at 20 liters per second, then here it's going to be 20 liters per second, if you assume that everything's moving at the same time, which in electricity they do. But we don't measure current like that in electricity. In electricity we talk about coulombs per second or amps, same thing. Coulombs per second or amps, exactly the same thing. And in a series circuit, they're always the same. This is always the same value. Always the same value for the current. If you measure, you put an ammeter here or you put it here, it's going to give you the same amount for the current. So current is equal at any point. There's a potential difference splits up over each component. So yes, in a series component, in a series circuit, the potential difference splits up over each component, which is what we were doing here, right? Here you have the 12 volts of the EMF, and we're saying that that will split between these light bulbs in equal amounts if they have the equal resistance, or unequal amounts if they have unequal resistance. In a parallel circuit, current splits up down each branch. So that's the opposite of here. Current is not the same. Current splits up down in each branch, and potential difference is equal across each branch. And that we spoke about here quite a lot, that the potential difference between here and there was both 6, but the current does split Here you will have some current, and here a different amount of current. Depending on what's on each branch, you will get more current in each one. The one with the lowest resistance always gets the most current. Okay, so that's enough for now, and I'll see you in the next revision video. Take care.